All right, so in section 5.3, we're going to talk about independence and the multiplication rule. So let's talk about independence first. So two events, E and F, are independent if the occurrence of E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of E in a probability experiment affects the probability of event F. So for instance, if we are picking names out of a hat and we have an entire class, if we pick, say, Bob out first, if we don't put Bob back in, then that's going to impact the probability of the next person being drawn. So that would be dependent. Whereas if we do put Bob back in, then the probability for the next person is exactly the same as it was on the first draw. So disjoint and independence, it doesn't mean the same thing. So disjoint means they don't share any common outcomes. So if we wanted to talk about, or you can't be both things at the same time. So for instance, you couldn't be male and female at the same time, or if you flipped a coin, you couldn't be a head and a tail. If you were drawing a card, you could not be a heart and a spade at the same time. Those are all disjoint. However, independence is talking about if the probability of one thing is impacted by another. So disjoint events are talking about if they can happen at the same time or if they share some of the same outcomes. And dependence or independence is discussing if one impacts the probability of the other. So let's look at a couple of examples and we're going to determine if these are dependent or independent. So the battery in your cell phone is dead. The batteries in your calculator are dead. Well, one does not impact the other. So the fact that the batteries are dead in the cell phone doesn't impact the batteries in the calculator and vice versa. So this is going to be independent. Your favorite color is blue. Your friend's favorite hobby is fishing. Again, one has nothing to do with the other, so these are going to be independent. You're running late for school, your car runs out of gas. Well, I would say there's a pretty high probability that those two have something to do with each other. So if your car ran out of gas, you're likely going to be late for school. So these are going to be dependent. Speeding on the interstate and being pulled over by a police officer, again, those are going to be dependent. If you're speeding on the interstate, you're going to be much more likely to be pulled over by a police officer. You gain weight, you eat fast food for dinner every night. And again, if you're eating unhealthy food every day, then that's probably going to contribute to a weight gain. So those are dependent. You get a high score on a statistics exam. The Boston Red Sox win a baseball game. And despite people being superstitious, these are going to be independent. All right, so let's look at B. So we have a box of 5 red and 4 green balls, a ball selected at random and is not replaced, and then a second ball selected at random. So if we go through and we select a ball and we want to figure out that the first ball is red, so the probability of the first ball being red is going to be 5 out of 9. So 5 out of the total of 9. So the probability of red on the first pick is going to be 5/9. And then we haven't put that back in, and the probability the second ball is red. Well, the probability the second ball is red, we have 1 ball missing, so we know that the bottom is going to change from 9 to 8 because we now only have 8 balls in. And as far as the top, it's going to depend if you drew a red ball or not. So if this first thing happened where you did draw a red ball, then over here it's going to be 4 out of 8. And if on the first draw you did not draw a red ball, then this would be 5 out of 8. So assuming that you did go through and draw a red ball, and then the second one you go to draw a red ball, you're going to have 4 out of 8 or a half. So you can see these probabilities are not going to be the same. And even if we had decided that you had not drawn a red ball the first time, this numerator turning to 8, these probabilities are not going to be the same for the first and second. So one does impact the other. So these are dependent. Now, if we go through and we replace the ball, so now the probability of drawing a red first ball is still going to be that 5 out of 9, but now the probability of drawing a red second ball, because we've replaced the red ball, we have the exact same circumstances that we did for the first draw, so it's still going to be 5 out of 9. So here, this is an example where it's independent. This is an example of it being independent. All right, let's talk about the multiplication rule for independent events. So again, independent events mean that one does not impact the probability of another. So if we want the E and F to happen, then we're going to multiply the probability of E times the probability of F. Now keep in mind that probability has to be between 0 and 1. So it can be 0 or 1, but usually it's going to be a number in between. So if we are multiplying two numbers that are between 0 and 1, we're going to end up with a smaller number. So what I mean by that, so you want to look at the probability that we flip ahead and on a first flip and flip a tail on the second flip. So this is two different flips. The probability of flipping a head is going to be 1/2. The probability of flipping a tail is going to be 1/2. So the probability of flipping a head and then a tail is going to be 1/4. So the 1/4 is less likely than either one of these events individually, which hopefully makes sense. So if you're thinking about going through and you want to flip a head and then flip a tail, you only have a 1 in 2 shot of getting ahead. So you have to hit that first before you even have a chance at successfully completing both tasks. Now this example is just for two events, so the probability of flipping a head and then flipping a tail, so on 2 flips, but you can have a whole list of them, and you're just going to multiply all the probabilities together. So for A, suppose that events E and F are independent. The probability of E is 0.3, the probability of F is 0.6. What's the probability of E and F? And again, the probability of E and F is just going to be the probability of E times the probability of F. So we're going to have that 0.3 times 0.6, which is going to give us 0.18. And again, we're ending up with a smaller number than either one of these individually. Okay, let's look at rolling a die. What's the probability of obtaining 4 1s in a row when rolling a fair 6-sided die? And we want to interpret that probability. So we want the probability of rolling a 1 and a 1 and a 1 and a 1. So that's going to be the probability of a 1 times the probability of a 1 times the probability of a 1 times the probability of a 1. And as you probably already figured out, this is the same for all. So the probability of rolling a 1, that's one outcome out of 6 that we're interested in. So a 6 times a 6 times a 6 times a 6th. Or we could have said 1/6 to the 4th power, which is going to give us 1 over 1,296. So I want to point out here that whenever you're trying to do the same thing over and over and over again, if it's the same probability for each time, so that it's independent events, then you're just going to take the probability and raise it to the number of times you want to repeat the event. So for instance, as a little side note over here, if I wanted to flip 10 heads in a row, so that's going to be the probability of flipping a head and a head and a head and a head and so on and so forth for 10 flips. Then I know the probability of getting a head is 1 out of 2. If I want to do it 10 times, then I'm going to do 1/2 raised to the 10th power, which is going to be 1 over 1024. All right, let's talk about basketball. So in a recent basketball game, a player who makes 95% of his free throws made 8 consecutive free throws, assuming free throw shots are independent, to determine whether this feat was unusual. So again, he's doing the same thing over and over and over again. And we know the probability of 1 free throw for this player is 65%, or that's 0.65. So the probability of 8 free throws is going to be at 0.65 to the 8th power. And we'll go out to the 4th decimal, so that's going to be 0.0319. And then it's asking, is this unusual? Well, because this is less than 0.05, so it's less than 0.05, then yes, it's unusual. Okay, now here's a game that nobody's ever going to play. So let's say that you have a game of chance where you want to flip a coin, roll a single fair die, and then choose a card from a deck of cards. What's the probability of the following outcomes? So we want to flip a head, roll a 3, and then pull a king of diamonds. So the probability of a head and a 3 and a king of diamonds is going to be the probability of a head times the probability of a 3 times the probability of a king of diamonds. So the probability of flipping a head, well, that's 1 out of 2. The probability of rolling a 3, that's going to be 1 out of 6. And the probability of pulling the king of diamonds, that's one particular card out of 52 cards in the deck. So you're going to end up with 1 out of 624. All right, let's do the same game, only this time we have different outcomes that we're after. So the probability of getting a tail and then rolling an even number and then getting a red card. So this is going to be the probability of flipping a tail times the probability of getting an even whenever you roll the die, and then the probability of pulling a red card. So the probability of flipping a tail is going to be 1 out of 2. The probability of rolling an even, before we reduce that, there's going to be 3 out of the 6 numbers we're interested in, because again, the die is 1 through 6, and the 2, 4, and 6 will be even. And the probability of getting a red card out of a deck of cards, well, 2 suits that each have 13 cards in them are red, so that means we have 26 out of 52 cards that are red, again, before we've reduced. So if we want to come down and reduce these, the probability of flipping a tail is still a half. The probability of rolling an even is going to be a half. And then the probability of pulling a red card will also be a half. So we're going to end up with 1/8. Okay, let's talk about at least. So the idea of at least actually will be a little bit challenging for some students. So at least means greater than or equal to. So at least probabilities are often computed using the complement rule. So if it's saying at least 2, it might be easier to just do 1 minus the probability of 1, something like that. And realize that the complement of at least 1 is none. So I think of it as the opposite for the complement. So the opposite of at least 1, so that's 1 or more. So for us, it's going to be none. It would be the opposite, or be the other part of it. At least 4 is the complement of at most 3. So at least 4 is 4 or greater. At most 3 is 3 or fewer. So to find at least 4, the probability of at least 4, we would do 1 minus the probability of at most 3. Well, the probability of at most 3 is going to be the probability of 0, 1, 2, and 3. So we would add those together and then subtract. Let's look at a couple of examples. Southpaws, so that's slang for a left-handed person. About 13% of the population is left-handed. If two people are randomly selected, what's the probability both are left-handed? What's the probability at least one is right-handed? So let's organize our information right quick. So it's telling us that 13% of the population is left-handed. So if you were to go through and randomly pick somebody, the probability you pick a left-handed person is going to be 0.13. Well, if you're not left-handed, we're going to consider you right-handed. So the probability of picking somebody that's right-handed or not left-handed, then that's going to be 0.87. And we know that because the probabilities have to add up to 1. So again, we're considering all people that are not left-handed to be right-handed. So if 13% of the population is left-handed, 87% of the population is not, which again, we're going to call right-handed. We're picking two people. So the options for picking two people would be that we get two left-handed people, a left-handed and then a right-handed person, a right-handed person, then a left-handed person, or two right-handed people. So the first question, what's the probability that both are left-handed? So the probability of picking a left-handed person and a left-handed person is going to be the probability of a left-handed person times the probability of a left-handed person, or the probability of a left-handed person squared. So that's going to be that 0.13 squared, which will be 0.0169. And then for the second part of the question, what's the probability at least one is right-handed? So at least one is right-handed. So that's going to mean one or more. So if you've gone through and kind of sketched out your options, well, here we have a right-handed, here we have a right-handed, and here we have two right-handed people. So we could go through, figure out the probability for each of these and add them up, or we can do 1 minus the double left-handed. So the probability of at least one right-handed person is going to be the same as 1 minus the probability of no right-handed people, so none. But again, we're going to rephrase this, that no right-handed people. Well, if you're not right-handed, we're going to assume you're left-handed. So no right-handed means that you're both left-handed. So that's going to be 1 minus, and we already figured out the probability here. So the 0.0169. And that's going to give us 0.9831. So to prove the point here, I'm going to go through and actually work out these probabilities. So the probability of the left-handed person is that 0.13 times 0.13. A lefty and then a right-handed person is going to be 0.13 times 0.87. The right-handed and then left-handed is going to be 0.87 times 0.13. And then two right-handed people is going to be 0.87 times 0.87. So if we go ahead and figure these out really quickly, again, this first one's going to be 0.0169. But let's look at the other ones. So we have 0.1131. This will be the same, the 0.87 times 0.13 will also be 0.1131. And then the probability for two right-handed people, we're going to do 0.87 squared and get 0.7569. So we're to go through and add these probabilities. So we want to go through and I'm going to add up these three probabilities to show that it's the same. So the probability of getting a left-handed and then a right-handed person, so about 0.1131. The probability of getting a right-handed person and then a left-handed person is going to be the same. So that, again, plus the 0.1131. And the probability of getting two right-handed people is going to be that 0.7569. which is going to bring us to 0.9831, which again is exactly what we got by doing 1 minus 2 left-handed people. All right, let's talk about some Christmas lights. So Christmas lights are often designed with a series circuit. This means that when one light burns out, the entire string of lights goes black. Suppose the lights are designed so that the probability of a bulb will last 2 years is going to be 0.995. The success or failure of a bulb is independent of the success or failure of other bulbs. So what's the probability that in a string of 100 lights that all 100 will last the 2 years? Well, it's telling us immediately that the probability that we're going to have a bulb last 2 years is 0.995. So the probability of having 100 lights last 2 years is going to be that 0.995 to the 100th power. And to 4 decimal places, that's going to give us 0.6058. And then for B, what's the probability at least one bulb will burn out? So for part B, the probability of at least one burnout is going to be 1 minus the probability of no burnouts. Because remember, the opposite of at least one is none. So 1 minus the probability of no burnouts. Well, if you have no burnouts, that means that all 100 of these are working. So we're going to have 1 minus the probability that all work, which is 1 minus that 0.6058, which is going to give us 0.3942. All right, let's work one more problem out. So in your homework, you're going to have something very similar to this. So among 50 to 55-year-olds, 33% say they have used a computer while under the influence of peer pressure. Suppose 4 50 to 55-year-olds are selected at random. We want to find the probability that at least one has not used a computer while under the influence of peer pressure for the first part, and then we want to find the probability that at least one has used a computer while under the influence of peer pressure. So this is a little bit confusing, so let's organize our information first. So the probability that somebody has used a computer under the influence, so we're going to put that they have used it under the influence, so UI, is going to be 33% or 0.33. So the probability of somebody not using a computer, so not using a computer under the influence, is going to be 1 minus this, or 0.67. Now, because students sometimes have problems figuring out exactly the at least part, I think it's a good idea to go through and start to list some of your options to get an idea of how this is going to look. So I'm going to use U for under the influence, so using a computer under the influence, and I'm going to use N for not for using a computer not under the influence, or not using a computer under the influence. All right, and it says that we're picking 4 people. So I'm going to start listing what our options would start to look like. So we could pick all 4, and maybe all 4 are under the influence. Or maybe 3 of them are under the influence, and 1 is not. Maybe the 4th one is not. Or maybe the 3rd one is not. Or maybe the 2nd, or the 1st. And then we would go through and pick 2 ends. So we would have U, U, and then 2 ends. And we continue down. Well, I know that the bottom, the very end of this, is going to be all ends. And then just above that, maybe there's one U and the rest ends. And this is going to continue on. So we know that from here down, we have at least one N. So we've got one N, and we'd have twos, and then all the possible ways to pull three, and then, of course, having all four be N's. And we know from here up is going to be at least one U. So let's look at our question again. What's the probability that at least one has not used a computer while under the influence? So at least one has not. So we're looking for the N's. So I see an N here. So at least one not using the computer is going to be starting here all the way down to here. And again, we could go through and do the probability for each one of these and then add it up. But that would just be a little bit silly and take quite a while. So instead, the probability of at least one N is going to be, it's asking the same as 1 minus the probability of no N's. And the no N's is the probability of all U's. So we're doing 1 minus the probability of all U's. So this is going to be 1 minus the probability of a U is going to be a 0.33. So the probability of somebody operating a computer under the influence of peer pressure is going to be 0.33 to the fourth power, because again, we're choosing 4 people. So 1 minus the 0.33 to the fourth power is going to give us 0.9881. And then for B, it's asking us, what's the probability that at least one has used a computer while under the influence of peer pressure? So we're looking for at least one U. Well, the U's start here, and they're going to continue all the way up. So all of these have at least one U in them. So the complement of that would be these N's. So the probability of at least one U is going to be the same as 1 minus the probability of no U's. And in this case, that's going to be the same as the probability of all N's. So that's going to be 1 minus the probability of an N is going to be that 0.67. So 1 minus that 0.67 to the fourth power. So we're going to get 0.7985. So my suggestion, whenever you're going through a problem that's dealing with an at least, if you're having a little bit of a hard time grasping what it's asking you for, I suggest drawing out a little sketch about your possibilities. And you obviously don't have to fill all of them in, because that would take quite a while, but we can go through and get an idea of what the complement looks like a little bit more easily this way.